Okay. All right. So today we will be starting static failure theory. As you know, based on your syllabus, you're supposed to have a quiz this week, but I'm taking it next week. So next week, Tuesday, you're gonna have quiz 1. All right. So
Dr. Abedin, is that going to be on the last
it's going to
the
be
sections?
on the mechanical design as well as the static failure theory, both.
Oh, okay. So it'll include this material. Okay, understood.
All right. So let's start the broadcast. So we're going to look at this. All right. So you all know, can anyone tell me the plane stress condition, like when do we consider plane stress condition? Can anyone tell me that? Plane stress condition from your strength of materials class? I mean, you can be wrong, it doesn't matter, but I mean, what you remember, just let me know.
Or Z.
Yes, Parnian, can you repeat?
When we are dealing with only X or only Y or only Z axis.
Okay, that's uniaxial loading. Anybody else? Amir? We couldn't hear anything.
Oh, I didn't see any.
Oh, Ben, who said it? Okay, Ben?
Perpendicular to a surface?
Oh, that's normal stress. Okay. What Pandian says is partially correct. If you only have loading in XYZ direction, yeah, you could, because in other direction is 0. But plane stress condition is when you have loading, no loading in the out of plane direction. That means if you have XYZ, for example, and if you have stress only working in the Y direction and X direction and 0 stress in the Z direction, we will call that a plane stress condition. And most of the time, you can assume the problem to be a 2D problem, all right? But in reality, as you know, you may have stresses in all 3 directions as shown by this figure here. I have stress in the Y direction, normal stress in the X direction, normal stress in the Z direction. Not only I have normal stresses, I have shear stresses. I'll draw it with a blue mark. I have shear stresses in all directions. Okay, so this is a 3-dimensional stress case. Now from your strength of materials class, 2201, we only talked about plane stress condition. That means there was no normal stress in the Z direction. We only had stresses in the X and Y, normal stresses. There was no stress in the Z direction. We only had stresses in the X and Y direction. And we remember the Morse circle you have drawn is just one Morse circle, right? And you, how many principal stresses did you have in that case? You always calculated 2, if you recall. That's because it's a 2D case. Excuse me. Okay.
Salute.
Thank you. Okay, it's a 2D case. That's why you only had two normal stresses, maximum and minimum normal stresses. So you calculated sigma 1 and sigma 2. But if you have a 3-dimensional case, just as in this one, where you have normal stresses in all 3 directions, you will have 3 principal stresses. Now, by the way, do you guys remember what principal stresses are? Anybody? Derek, your mic is on. You can share that.
Share what?
We didn't hear anything, Derek.
Share what?
Share with us what principal stresses mean.
There's some sort of stress.
What sort of stress? You cannot, at this point as an engineer, you cannot say some sort of stress.
I don't know.
Is anyone willing to help Derek out? Yes, Art?
So would principal stress be the stress that's on the x-axis only?
No, principal stresses are normal stresses. It doesn't need to be acting along the X or Y axis. It will be at a specific direction. So if you recall, let me see if I have any space.
Like along a face, correct? Like the ones in blue?
Say for example, you have this case. This is Y, X direction, this is Y direction. So if you remember, if your stresses are, if you are rotating, so for example, in this plane, you have sigma X, sigma Y, you have shear stresses as well. Now, if you rotate this plane, now the plane is something like this. You rotated it about the x-axis, for example. Now you have a new x-axis, which I will call it to be x prime and y prime axis, okay? And say, for example, at this orientation, you are only looking at normal stresses, no shear stresses. So I'm going to call this sigma x prime, sigma y prime. And there is no shear stress. You will see that these normal stresses turns out to be the maximum and minimum normal stresses this particular plane will see, okay? Those are called our principal stresses. So principal stresses are, so if you recall my strength of materials class, what we have covered last, I think a lot of you took that class this spring. So as you rotate the plane, the stress values for different directions, the stress values changes. Say if I go this way, that's bad. If I go, I mean, if you rotate the planes for different rotation, you're going to end up having different stresses, values of stresses. At one orientation only, you're going to see that there is no shear stress. There's only normal stress. And of all the orientations, for that particular loading case, that orientation has the maximum or minimum normal stress. And we call that the principal stress. Do we understand this now?
So it's defined by not having a shear stress for sure?
Oh yeah, principal planes do not have shear, in-plane shear stress. No, they do not. But it is more, but the definition, the correct definition would be, it is the maximum or minimum normal stress and a certain structure is going to see. Okay, and it happens that when you go to that orientation, you do not see the shear stress. Yes, Jesus, you had a question.
No, I'm actually fine. You ended up answering.
Okay, so remember our goal in this, in strength of materials, our goal was to calculate what will be the stress at various orientation, how you calculate them. But for the machine design, we're designing something. For this case, our goal is to be able to come to a conclusion whether the structure is going to fail or not. So we are a lot interested in either maximum shear stress or maximum normal stress. If you're dealing with maximum normal stress, that's the principal stress. Okay, so for a 3D case, you're gonna have 3 principal stresses and they're designated as sigma 1, 2, 3. And sigma 1 is always larger than sigma 2. Sigma 2 is always larger than sigma 3. This is how they are, this is how the series goes, okay? So for 3D case, you have 3 principal stresses. But if you have a plane stress condition where you do not have any stress out of plane that is in the Z direction, then you are dealing with 2D case, and you are going to have only 2 principal stresses. Do we understand this, people?
May you repeat that last part?
So if you do not happen to have this sigma z, you only have sigma y, sigma x, and the shear stresses in the xy plane, something like that, then you're going to see 2 principal stresses, sigma 1 and sigma 2. But the moment you have sigma z, you're going to see 3 principal stresses, sigma 1, 2, 3. Does that make sense, people?
Yes.
Yes.
Okay. It is very important to get that cleared. Now, for our case, how many stress components do we have? You will see that for a 3D case, you're gonna have 6 stress components. 3 stress components will be normal stress. So sigma xyz will be normal stress. You will see that tau xy is equal to tau yx. Tau yz is equal to tau zy, and tau zx is equal to tau xz. So you're going to end up having 3 shear stress components. So you have 3 normal stress components, 3 shear stress components, okay? Now, if you want to draw your Mohr circle for this, so you can see that you're going to have 3 Mohr circle, okay? The first one is your, the first one is the AB Mohr circle. I'm drawing it with my orange color here. Okay, you will see that this is my sigma 1 from here all the way, whatever you read, that's my sigma 1. Okay, this will be my sigma 2, the x-axis reading, that means from here to here. Now the sigma 3 would be, so you have 3 Mohr circle. One is the AB, the other would be the AC. AC, I'm gonna draw it with a blue line. And then BC with a red line. Now this C point will give you the sigma 3. Okay, that's the third principal stress. Okay, so sigma 1, 2, 3. Now you're gonna have 3 maximum shear stresses. Okay, we're calling them principal shear stresses. One would be this one, tau 1, 2. The other would be tau 1, 3. And the other would be tau 2, 3, which is this one. So you have 2, 3 maximum shear stresses, and you can calculate them using these using the principal stress values. Using
Professor?
these, yes.
Sigma 1 and minus sigma 2 over 2, that wouldn't that just give you the center point of the circle?
Yes.
But how do you
will.
get the radius then?
That would be the radius.
No, that will be the radius. I mean, if you look at it, this is your sigma 2, right? This is your sigma 1. Sigma 1 minus sigma 2 divided by 2 will be half of this, which
Okay.
is the
Yep.
radius.
Yep. All
So
right.
that will give you the radius.
Don't worry about me. Don't worry about me.
So all these maximum shear stresses are nothing but the radii of the 3 circles you see here. Okay, and you can calculate them using these principal stress values. All right, so this is in 3D. So we will be using these principal stresses and maximum shear stresses a lot. Now let's look at failure theories. So hypotheses for failure were developed over time. Materials, you're going to classify it as ductile or brittle material. If the strain at failure is greater than 0.05, we classify it as ductile material. If it is less than 0.05, we'll classify it as a brittle material. Okay, and based on whether the material is ductile or brittle, we're gonna choose our failure theories. So we have 3 failure theories for ductile material: maximum shear stress, distortion energy, ductile Coulomb-Moore theory. For brittle materials, again, we have 3: maximum normal stress theory, brittle Coulomb-Moore theory, modified Moore theory. Okay, so we have 3. So you're going to start with ductile material. Okay, so maximum shear stress theory for ductile material, MSS. Okay, sometimes you will see they call it Tresca or Guest theory. In other books, you might find the same theory as Tresca theory. Okay, so let's look at, it's a very conservative theory. Okay, it's conservative predictor of failure. And that's good. If you want to, a lot of the time people like to be conservative when they're designing things just to keep things safer. So it's a very conservative theory. What it states is, very carefully listen to me, yielding occurs whenever maximum shear stress equals or exceeds the maximum shear stress in tension test specimen of the same material when at the yield point. Now, what does that mean? Let's just go through this. So you have this tensile specimen. Let me draw a proper tensile specimen. So this is your dog bone tensile specimen. Okay, you're in a tensile test. What do? You pull it, apply normal load, and that means you're applying normal stress, right? So you're pulling it. Now you keep on pulling it, say, until your specimen starts yielding. That means you reach your yield point. Okay, when you reach your yield point, obviously the maximum shear stress that you will see for this case, so the maximum shear stress that you're going to be seeing here, okay, when it reaches this yielding point, then say that value is tau, I'm going to call this a tau t, okay, that value is tau t. And for any structure, for example, made of the same material, if the maximum shear stress becomes equal to this tau t, then we are going to say that, hey, the material yielded, it failed. Okay, so does that?
So is this when necking, basically when you start seeing necking, that's your value
So
when
necking,
you're saying?
remember, no, necking is beyond yield point. Remember, necking starts at when? Ultimate tensile strength, not at yield point.
Okay.
It's way below necking. Okay, when your material just starts to undergo permanent deformation, when you are conducting this tensile test, then the maximum shear stress that you're going to be seeing, if for any structure made of the same material reaches that shear stress value, then we are going to say it failed. Okay, yielding occurred and it failed based on this Tresca theory or MSS theory.
Right, but for engineering purposes, we use the 0.0, the 2% offset, right? I mean,
Offset, yeah, offset for when it reaches that offset value.
okay, I
Then
see what you're saying.
then the maximum shear stress you see for the tensile test case, if your actual structure reaches that maximum shear stress, doesn't have to be under tension, this uniaxial loading, it can be in any loading. If it reaches that value, then we say that, okay, the material failed or the structure failed. Okay, so let's look at this. If you remember from your strength of materials, when whenever you apply load like this, whenever you're applying load like this, so what type of loading is this, people who can tell me? Jack, I didn't hear.
Transverse loading.
Sorry?
Tensile.
Axial loading.
Tensile axial loading, yes. It's uniaxial tensile loading, right? Uniaxial means you're only applying load along one axis, okay? So it's uniaxial tensile loading, okay? That's what you do in your tensile test, right? So in this case, if you remember from your strength of materials, chapter 1 or 2, I don't remember which chapter, any one of them. Remember this formula for if you have a plane like this versus a plane which is inclined, how do you get the shear stress? So if you say cut a plane at an angle, the new plane will look something like this. So for this case, what do you see? You have the tensile loading, but now along this inclined plane, you can, so if this load is P, you can actually resolve it into shear loading as well as normal loading. So the inclined plane sees what? Both shear and normal. Whereas this cross section sees only normal. Do we understand these concepts now?
Yes.
Great. So for an inclined plane, if you remember, this was the formula. Theta, where theta is the angle. Okay, P is the applied load, and A is this cross section. This cross section is my A. Okay. All right. So when will your, so in a tensile test, so this is the same as doing tensile test, right? So in a tensile test, based on this formula, when will you see maximum, at what angle will you see maximum shear stress?
45
5.
45 degree, correct. And that value, then your maximum shear stress becomes P by 2A, right? So P by A is the sigma stress you're applying. So half the normal stress is the maximum shear stress you see in a tensile test. Do we agree?
Sorry, one more time on that last sentence.
Yeah. So in case of tensile test, half sigma is what? Normal stress, which is P by A. Okay. So the maximum shear stress happens at 45 degree and its magnitude is half the applied normal stress. Based on this formula. Do we agree?
Yeah.
I only raise your hand if we agree. Let's see how many of you agree.
I agree.
I forgot how to raise my hand, but yeah,
I agree, but
Yeah,
I don't know
where's
how to raise my
the
hand.
raise hand thing
Okay,
again?
that's fine as long
I'll
as you are
agree.
talking.
Doesn't mean I understand.
What? No, you have to understand if you agree. You cannot agree with anything without understanding.
You go to participants and you go to your name.
Hey, you didn't say that was part of the deal.
Okay, so
How many of you understand? Raise your hand now.
I'm
You do that.
You go to participants, and then once you click on participants, all the list comes up, and then there's a little button on the side that says raise hand.
Thank you. Okay, I can see a
Oh,
lot of you
cool.
are raising hand.
I don't know
Okay.
if that means much.
Thanks, man.
Amer, you don't seem to raise your hand. Angelica, you do not so those who did not raise your hand.
Sorry, I raised it, then I put it down.
Okay.
Okay.
All right. Derek, do you understand?
So the shear stress is half of the normal stress at the 45 degree
45
maximum
degree plane.
Yeah, that's 45 degree
when
plane.
you are doing tensile test.
Uniaxial
It's
tensile.
only for tensile testing. Do we understand this? These formula that I have written is applicable for uniaxial tensile loading. That means a tensile test.
Good.
Good? Okay, that's good. Now remember this theory we were talking about? This theory said, hey, during tensile test, during the tensile test, when you reach the yield point, what is your normal stress? So when you reach the yield point, you keep, what do you do in a tensile test? In a tensile test, you're pulling it, right? Pulling it with incremental load. So this is my test specimen and I'm pulling it with incremental load, right?
You were
So,
saying what happens once the load it's hit the yield point?
yeah, when it hits the yield point, then the normal stress becomes equal to what? Yield strength. Then the normal stress becomes equal to yield point. Then the maximum shear stress, instead of writing sigma by 2, I can write SY by 2. In your book, SY means yield strength. In your book, SY, sigma, Y are same. So anytime if you know the material's yield strength, okay, and you're using this material for some structural function and you're applying load to that material, if during load analysis, if the stress reaches half the yield strength, then we're going to say, hey, according to Tresca theory or MSS theory, the structure failed. Do we understand the theory now?
Yeah.
Okay.
Professor?
All right. Yeah.
Well, sorry, I just lost my train of thought. Will we say the material failed when we finally see permanent deformation? Is that the assumption?
Can you repeat the question, please?
Can we say that the material failed when we see any kind of permanent deformation?
Yeah, definitely. But
Okay,
in your analysis, you have to follow a failure theory, right? So this is the theory. You're going to do stress analysis and you're going to see that whether anywhere in the structure, the stress exceeds half the yield strength or not.
Okay.
Not any stress, whether the maximum shear, whether the shear stress in the structure exceeds half the yield strength or not. If that is the case, then we say yielding occurs. That means permanent deformation occurs and the structure has failed, okay? So it's not just any stress. We're talking about shear stress here. So that's why the name of the theory is maximum shear stress theory.
All right, thanks.
So let's look at this. Maximum shear stress theory for ductile material in 3D. Okay, so we are saying, hey, so the tau max is going to be, so let's look at this diagram again. Tau 13 is maximum, right? Tau 13 is the maximum radius we see for these circles. More circles here. Do we all agree?
Yes.
Yes.
Okay. So tau 13 is how much? Sigma 1 minus sigma 3 divided by 2. So so the tau max for any structure is going to be this equation. Will give you the maximum shear stress in any structure where sigma 1 is greater than sigma 2 is greater than sigma 3. Sigma 1, 2, 3 are your principal stresses. And based on the maximum shear stress theory, I'm saying, hey, yielding occurs if this maximum shear stress exceeds half the yield strength of the material. That's what I'm saying. Okay, so I can write, hey, if sigma 1 minus sigma 3 divided by 2 exceeds or becomes equal to half the yield strength, then we're done with the structure. It failed. Okay, so 2 will cancel out. So we are only left with sigma 1 minus sigma 3 greater than or equal to SY, which is your yield strength. Okay, so for your design, what do you have to do? This is when failure happens. Failure. So for your design, you have to keep this less than the yield strength. So that's what I'm saying for your design. So if we put them equal, say tau max is equal to yield strength, half the yield strength divided by 2. Okay, if then your factor of safety will be 1. Okay, but if you want to keep higher factor of safety, then it should be SY by 2 divided by tau max. So
But
this will give you this equation.
hey, Professor.
Yes.
So when you go to your Moore circle again, and like there's a bunch of smaller circles.
Yeah, but we are interested only in the maximum shear stress. Which circle has maximum radius?
Okay. So, but
AC, right?
yeah, I mean I see
Yes.
that 1 and 3, but won't 1 and 2 have a smaller value though? Like,
yeah, but as long as your maximum value is less than half the yield strength, then obviously the smaller ones are less than half the yield strength. They won't cause any failure, right?
Okay.
All we want is to know whether it's gonna fail or not, right? Do we understand this?
I do now. Thank you. Sorry. Sorry for
So, so this is the formula ultimately. Maximum shear stress is equal to yield strength divided by 2n, where n is your factor of safety. Or if you don't want to write maximum shear stress, say you want to write sigma 1 minus sigma 3 divided by 2 is equal to sy by 2n, 2 cancels. This gives me a formula of sigma 1 minus sigma 3 is equal to yield strength divided by factor of safety. So basically this is what I end up having. So if you want to know for any structure, if it is ductile, if you want to use the most conservative theory, that will be your Tresca theory. And if you know the principal stresses and yield strength of the material, you can easily calculate the factor of safety. If the factor of safety is less than 1, you know that, yes, the structure is not going to survive. So for any analysis, what do you have to do? You have to do a stress analysis. You have to find out the principal stresses, and then only you can make that conclusion.
So just to clarify, we would get the SY from them telling us what our
Then
yield
means
is.
you are the engineer, you design. You're gonna choose the material. If
Yeah,
you don't
that's why I was asking. We would choose the material which has a certain yield strength, right?
correct. If you do not know the yield strength of the material, what do you have to do?
Test it to find out.
Yes, what type of test?
Tensile test.
Very good. Tensile, yeah. All right. Maximum shear stress theory for ductile material in plane stress condition. Now, plane stress condition. What does this mean, people? One of your principal stress is 0.
0.
Right? You have sigma 1, sigma 2, sigma 3. One of the principal stress will be 0.
We're working in a 2-dimensional plane.
Correct. So one of that will be 0, but this is how you're going to arrange your cases. You'll have 3 cases, case 1, case 2, and case 3. Okay. So for case 1, say you have your sigma 3 to be 0. And your sigma 1 and sigma 2 are both positive. And they are arranged like this. Sigma 1 is greater than sigma 2 is greater than 0. That means sigma 1 and 2 both are tensile stresses. That's why they are greater than 0. Okay, if that is your case, then this is the formula you can use. Then you're going to put sigma 1 equal to sigma A. Sigma 2 will be equal to sigma B. And your sigma 3 will be 0. And if you plug in, remember our formula is what? Our formula was sigma 1 minus sigma 3 is equal to Sy by n. Okay, sigma 1 would be sigma A, sigma 3 is 0. So sigma A is equal to Sy by n. So this is what you see. Again, if for your second case, you have one of the normal stress, principal stress to be tensile, the other principal stress will be compressive. So your case will be something like this. Sigma 1 is greater than 0, but sigma 3, but 0 is greater than sigma 3. So sigma 3 is compressive, sigma 1 is tensile. If that is the case, you're going to put sigma 1 is equal to sigma A, sigma 2 will be 0, sigma 3 will be sigma B. And if you plug in, this is what you will see. Sigma A minus sigma B is equal to yield strength divided by factor of safety. Let's look at case number 3. In case number 3, the two principal stresses that you have both are compressive in nature. Okay, so both are negative. So in that case, your sigma 1 is 0. Then you'll have the next higher sigma stress, and then sigma 3 will be the remaining one. Okay, that's how you're going to arrange your case like this. Okay, so sigma 1 is 0, sigma 2 you're going to put it as sigma A, sigma 3 you're going to put it as sigma B. Now sigma 1 is 0, so it's 0, sigma 3 is sigma B minus sigma B is equal to Sy by N. So sigma B is equal to negative Sy by N. This is what you see. Okay, so these are some of the formula you would definitely put in your formula sheet. Now we're going to look at what is called the distortion energy theory for ductile materials. You're going to see this. This theory is used a lot. It is a more common theory to use. So this is the distortion energy theory, DE. Okay. So what does it say? It is also known as von Mises-Henke theory or shear energy theory. And you'll come across this load, von Mises stress, a lot. Okay. So especially if you're doing a finite element analysis, you'll see that people look at von Mises stress a lot. That means they're actually using the distortion energy theory for their design. So let's look at this. Whenever you have a load, a triaxial loading. So what do I mean by triaxial loading? So if you have a box like this.
There's forces in all three directions, including the
What
Z.
type of forces? You cannot, at this point, you cannot just.
Normal forces.
Good. Normal forces or normal stresses in all three directions. You're right, that's triaxial loading. What happens when you have triaxial loading? You're gonna see two things.
We're gonna see three shear and three, what did I write? 3 shear components and 3 normal.
Okay. Hold on a second. The 3 stresses that that are being shown here. What type of stresses are these?
Normal.
Okay, normal. Are they principal stresses?
Yeah.
No.
How many of you say yes? Raise your hand. Now that everyone knows how to raise their hand. Everybody thinks, okay, I can see.
No, I
know my hand was already raised.
I can see half of the class raising their hand.
I don't think they're principal stresses.
Okay, since Jesus thinks he doesn't, they are not principal stresses, would you like to share with us why you think that way?
Well, I thought by, if you're looking at it in a 2-dimensional way, wouldn't the third
you
one...
cannot look at it in a 2-dimensional way. You're applying three.
I'm just saying, if you're looking at one of the faces, wouldn't the third axis cause shear stress on the other two?
Okay.
Could be 0 though, the third one.
Yeah, as you can see that in this orientation of the box, you do not have any shear stress. You only have normal stresses. So these are the principal stresses. If you are rotating the box by some angle, then you're gonna see both shear or normal, shear and normal, both stresses. But in this case, at this orientation, I did not draw any shear stress here, right? For this box. I did not draw any shear stress in this box, only normal. That can only mean one thing. The normal stresses here are principal stresses. Okay, so whenever you have triaxial loading, you're gonna see two things. One, you're gonna see an angular distortion. The box is not going to stay perfectly like this. It's not gonna stay like this. It's going to get distorted because you just applied load, right? And also you're gonna see change in volume. So you're gonna see two things. One is the change in volume. The other is the angular distortion. Now, the stress that causes change in volume is the average of the three principal stresses that are being applied. Okay, that's the, we call that hydrostatic normal stress, because you only see normal stress here. You do not have any shear, okay? So this is my hydrostatic stress, normal stress that causes change in volume, which is nothing but the average of all three principal stresses. So this is the hydrostatic component, and the remaining stresses, which is sigma 1 minus the hydrostatic component, sigma 3 minus the hydrostatic component, sigma 2 minus the hydrostatic component. That is my distortion component causing distortion of the structure. Do we understand this?
Just a question.
Yeah.
So would any object with three normal stresses always cause change in volume and angular distortion?
It should, yes.
Okay.
So based on the distortion energy theory, we, if you want to calculate the strain energy per unit volume for tension, this is the formula. Okay, that is equal to U is your strain energy. That's equal to half the product of stresses and their corresponding normal strains. So sigma 1 times epsilon 1 plus sigma 2 times epsilon 2 plus sigma 3 times epsilon 3. That will give you the total strain energy. Now, if you want to replace this strain with sigma 1, remember from, if it's a triaxial loading, from your strength of materials, let me see if I have those slide here, because I just took that class. Okay. Stress transformation, torsion, Poisson's ratio. Okay, good. Triaxial loading. This is from my strength of materials course. If you remember, you all have it. You all should have it. If you remember, this is how in triaxial loading, I'm just applying normal stresses in the XYZ direction. And in the X direction, this is the strain. Okay, in the Y direction, this will be the strain. Does that ring a bell to you all? In the Z direction, this is my strain value. Does this ring a bell to you guys? Or you all forgot?
In these pictures does.
Not really.
So if you remember,
Yes, I remember this question. I missed it on the test. Yes.
So if I want to know the strain in the X direction, Strain in the x direction will be caused by the sigma x definitely. And from Hooke's law, we will know that. So for the x direction, okay, the axial strain is going to be sigma x by Fe. That's my axial strain. Sigma x will cause axial strain, whereas sigma y and z will cause transverse strain. Do you guys remember? So for the transverse strain, you have to multiply with Poisson's ratio. Do you guys remember that?
A little bit, yeah.
Okay.
So what does the big E stand for? Sorry, forgot what that was.
That
Elasticity.
E is your modulus of elasticity.
Right.
So if you go back to, if we come back to our current lecture, okay, so if I can say, hey, in the one direction is say my x direction. So my epsilon 1 is going to be sigma 1 by E minus Poisson's ratio, sigma 2 by E minus Poisson's ratio, sigma 3 by E. That's my strain in the total axial strain in the one direction. Similarly, if you want to write down sigma epsilon 2, you can write it down as minus mu sigma 1 over E plus sigma 2 over E minus mu sigma 3 over E.
So, Professor, I have a question.
Yes.
What are the units of strain energy? Is it joules per meter cubed or?
Yes.
Okay. Is this like measuring basically like how much?
How much energy is being stored? If you are straining something.
Okay. Like a stored energy stored in a spring. Okay.
Something like, yeah, that concept. Yeah. Yes. So instead of writing sigma 1 here, sigma 2 here, sigma 3 here, if I write it in terms of, sorry, not sigma, epsilon 1 here, epsilon 2 and epsilon 3, instead of writing them in terms of strain, I can write everything in terms of stress, sigma 1, 2, 3. If that is the case, this is the expression that you will get, where mu is your Poisson's ratio. This E is your modulus of elasticity, and sigma 1, 2, 3 are the principal stresses. Okay? Do we understand this, people? I'm just showing you the derivation.
Squared plus
forward.
Yeah, it is coming by replacing sigma 1 is equal to these expressions.
Just
Epsilon 1, not sigma 1.
Just to verify, that V is specific V, right?
That V is actually your Poisson. The mu is same as the V here. It's Poisson's ratio. It's not actually V. It looks like a V, but it's a Greek.
Oh, okay.
All right, now let's move forward. Strain energy per unit volume for producing only volume change. So if we want to see only volume change, then we are going to replace this sigma 1 plus sigma 2 plus sigma 3 divided by 3 is equal to sigma average. Okay, so we're gonna, instead of sigma 1, 2, 3, we're gonna plug in sigma average, because the stress component that causes distortion is sigma average. So we're gonna plug in sigma average, and if you plug that in, you're gonna end up having this formula. Okay, so instead of, so for strain energy per unit volume for producing only volume change will be, instead of sigma 1, 2, 3, you're gonna put sigma average, and this is the formula you get. Okay. Now you can expand sigma average as sigma 1 plus sigma 2 plus sigma 3 divided by 3. So if you want to replace sigma average with sigma 1, 2, 3, This is what you will get. So this, let me highlight it in yellow. The yellow formula gives us the strain energy for volume change, and the green highlighted formula gives us the total strain energy. Okay, so what will be the distortion energy per unit volume? Distortion energy per unit volume will be total strain energy minus the strain, the volume change strain energy. That means strain energy only for volume change. So that means if you subtract the yellow highlighted formula from the green highlighted formula, then you will get your distortion energy per unit volume. And it turns out to be this one. Let me highlight it in blue. This is my distortion energy. Now you might be thinking, why is she spending so much time in making us understand distortion energy? That's because now we're going to go in, dive into the theory. What does the theory say? We're going to dive into the theory. The theory says that yielding occurs when distortion strain energy per unit volume reaches or exceeds the distortion energy per unit volume for yield in simple tension test or compression test of the same material. That means when you do tensile test or compression test, okay, when you do that, the distortion strain energy per unit volume that you get, okay, in the actual case of the structure, if the distortion strain energy per unit volume exceeds that value, then we say the structure has failed. Okay, so let's look at this. For simple tensile test, what do we have? When the simple tensile test, you only have one stress. Remember, for simple tensile test, what are you doing? You're just pulling it like this. So you're applying only one stress. There is no sigma 2, there is no sigma 3, they are all 0. So you can see that sigma 2, 3 is 0 for a simple test. You only have sigma 1. And when it reaches the yield strength, then sigma 1 becomes equal to your yield strength. So for that case, your distortion energy becomes, so if you put sigma 2, 3 for this particular blue highlighted formula, if you put sigma 2 to be 0, sigma 3 to be 0, this to be 0, sigma 1, you're going to put it as SY, sigma 1 will be SY, sigma 2 will be 0. If that is the case, okay, you end up having, so from here you can write down UD becomes equal to 1 plus mu 3E times 2SY divided by 2SY square divided by 2. 2 cancels out and you end up with this formula. And this theory states that, hey, yielding will happen. This formula is only in case of tensile test when sigma 1 is equal to yield strength. This is the formula. This is the distortion energy in tensile test when the applied stress becomes equal to your yield strength. Now the distortion energy theory tells you that, hey, for your structure, I'm going to erase all of this. For your structure, how do you calculate? You have a structure where the loading is not tensile loading only. You have all sorts of loading, say 3-dimensional loading, you have shear, whatnot. For your structure, calculate the distortion energy. So this is the formula you will use to calculate the distortion energy for your structure of interest. And if that distortion energy, okay, yielding happens, if that distortion energy becomes greater than your distortion energy in the tensile test. So when this red boxed equation becomes greater than this green boxed equation, then we say that, hey, your structure is going to fail. So if I do this, let me see if I have any space to do it. Okay, so let's write this down. If I write this down, it's going to be 1 plus mu 3e. Then I have what? Sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square divided by 2. Okay, that becomes, that is greater than your 1 plus mu. I'm going to erase all of these. 1 plus mu divided by 3e times sy square. Now this 1 plus mu 3e cancels both sides. Okay, and if you take square root on both sides, then you end up having sigma 1. So I end up having a half here, and this square disappears. So yielding happens when this quantity is same as this quantity that I have, is greater than or equal to your yield strength. Then yielding takes place. Now this quantity, I'm going to highlight it in yellow. This quantity has a special name. It is called...
Wait, which one did you highlight? I'm so sorry.
I'm going to highlight it in red.
Oh, okay, my bad.
This quantity has a special name. We call it von Mises stress. And we say that, hey, if your von Mises stress exceeds your yield strength, then your structure will fail. And we designate this entire quantity in this green box, which is highlighted in red. We designate it as sigma prime. So you can see later during here, I'm writing, hey, if sigma prime is greater than the yield strength, then your material, your structure will fail. Where sigma prime you will calculate using this formula, and it is called von Mises stress. Now, if you want to, for design purpose, what do you have to do? You have to keep the von Mises stress less than the yield strength. Then only you will know that your structure will not fail. Okay, so how do you calculate, or you can say, hey, I want to introduce a design factor. So if you want to introduce a factor of safety, then von Mises stress is equal to yield strength divided by factor of safety. As long as your factor of safety is greater than 1, we know that the structure will not fail. Now, how do you calculate? So the main thing, if you want to use distortion energy theory, what do you have to know, people?
Yield strength.
Can you speak a little loudly?
The yield strength of the
Yeah,
material.
yield strength of the material. Then
The Poisson's ratio.
do you need the Poisson's ratio?
No, not for this specific case, right? You just need the sigmas, the principal stresses.
Correct. You
the
just
von
need the
Mises.
principal stresses. If you know the principles, that's why it is so important. If you know the principal stress of your structure, you can easily say, hey, whether it's going to fail or not. Use any failure theory and make your conclusion whether it will fail or not. But you need to be able to find the principal stresses, because in reality, nobody's going to give you the principal stress. You have to calculate it. So say if the principal stresses are not given, for that case, you can use, say it is given in terms of shear stress and normal stresses. Okay, sigma x, y, z, tau xy, tau yz, tau xz. Then you can use this for 3D state. You can use this formula. Life is easy. Okay, and if you have plane stress, life is even easier because sigma 3, in that case, you only have sigma z is 0, tau xz and yz are 0. You only have sigma x, sigma y, and tau xy. And you can easily calculate it directly. Or the other way would be in your stress transformation in the strength of materials class. Let me see if I have stress transformation. I remember seeing it somewhere here. Beam deflection, simply state of stress. Okay, this is my strength of materials lecture. So if you wanna know, if you know sigma x, sigma y, and tau xy, you can directly calculate principal stresses using this formula. Okay, once you know the principal stresses, all you have to do is go back. Let's go back to our final. All you have to do is plug those sigma 1, 2 in this formula. Okay, and sigma 3, any one of it will be 0, and plug in the remaining 2 principal stresses, you'll get your von Mises stress. Or if you are lazy, you don't want to do that, you can directly calculate your von Mises stress from here. All right, so these are very important formula. So distortion energy theory for ductile material. Okay, so any question before I move forward? Any question, people? You all sound really quiet.
No, you're good.
I think we're just
It's a lot of material.
Yeah, we're just taking it all in.
Do you guys want me to post the lecture slide for state of stress from strength of materials
Yes.
class?
Yes,
Oh
please.
yeah, please.
Yes, please.
Yes.
I will post that. Okay. All right, so this is something to think about. I'm just trying to connect everything. I'm just trying to make you think how strength of materials is connecting to this class. I mean, I don't want you guys to learn everything without understanding. All right. All right, let's look at this. As I have mentioned, remember the maximum shear stress theory is more conservative. So that's what I'm gonna show over here, that maximum shear stress theory is more conservative than the DE theory, that is the distortion energy theory. And we're gonna show it here, okay? So in order, for the purpose of showing that, we're gonna say, hey, an element is under plane stress condition and pure shear. That means you have a stress element like this. There is no out of plane stress. You only have 2D case and you do not have any normal stresses. You're only applying pure shear. Okay. If that is the case, then sigma x and sigma y is going to be, people, 0. You do not have them. So if that is the case, let's plug in to this formula. Sigma x is 0, sigma y is 0. I only have shear stresses. So my von Mises stress turns out to be sigma prime 3 tau xy square to the power half. This gives me something like √3 tau xy, right? So this is exactly what I have. Okay, so yielding happens based on distortion energy theory. Okay, yielding happens when sigma prime is greater than or equal to yield strength, right? So instead of sigma prime, I can write here, for our case, it is root over 3 tau xy, which is same as what I have here, okay? This is what I have. So we can say, hey, tau xy is greater than or equal to sy by root 3, right? So the shear stress is greater than or equal to, so 1 over root 3 is same as 0.577 yield strength. So I'm going to say, hey, shear stress when it exceeds, when this applied shear stress, this is my applied shear stress. If the applied shear stress exceeds 0.577 times of the yield strength, well, we are seeing failure. So in order to avoid failure, what do I have to do? I have to keep this applied shear stress less than or equal to 0.577 times the yield strength. Do we agree with this, people?
Yes.
Okay, now let's look
What
at...
was the percentage? What was the percentage of failure for the maximum shear stress
I'm
theory?
going over it now. Now for the maximum shear stress theory, okay, what it was, how, look at this formula. The shear stress has, you have to keep the shear stress less in order to avoid failure. 50, yeah, in order to avoid failure, your shear stress has to be less than or equal to half the yield strength, which is 0.5. Instead of writing sy by 2, I can write 0.5 sy, right? So if you were using, for this case, for this particular case that I'm talking about, if you were analyzing it with the maximum shear stress theory, you're gonna say, hey, if the applied stress is less than half the yield strength, we're good, okay? But if you are using distortion energy theory, you're gonna say, hey, if the applied shear stress is less than 0.577 times the yield strength, then we are good. That means with distortion energy theory, you can apply a little more higher shear stress than if you were using the maximum shear stress theory. So which one is more conservative? The maximum shear stress theory is more conservative. Do we understand this?
Yeah.
Yes.
Yes. Oh, that's good. Yes. Good. All right. So we are almost to the end of the class. Hopefully next class, I'm going to finish this and then go to the, yeah, we don't have much, we don't have any, we have a few slides left. I'm going to finish this and we're going to do a worksheet too. That's going to take some time. And on Tuesday, you will have your quiz, 15-minute quiz online, Blackboard. It will appear on Tuesday. And it will be there until the end of day on Wednesday. You can, so you can either take it on Tuesday or you can take it on Wednesday. But once you start taking the quiz, you have to finish it. So it's a 15-minute quiz, very short, basically very short questions, trying to probe whether you understand the concepts or not. All right, I will also, yeah.
Professor, are you gonna post an announcement about what the quiz is gonna cover?
Yes, I will.
All right.
I will. John Torres, if you're here, please stay back. And yeah, if you guys have no question, here Vin is asking when stress is at the maximum or minimum. Vin, what do you mean by that?
I
Vin, I
think that
can't
was a
hear you.
response. I think that was a
That
response
was like an
for
hour
earlier.
ago.
Yeah.
Yeah, I just saw it. It was from an earlier question. So do you understand it now?
Sorry, it was like, who the fuck knows an actual Jamaican? Except, I think Brandon.
Okay. Vin, do you understand it now? Just chat. Oh, you were answering. Okay. All right, people. In that case, we're going to end the class here if you guys have no question. John Torres, please stay back. All right, I'm
Professor-
ending the recording here. I'll see you all on Thursday.
Thank you.
Thank you.
Thanks, Professor.
Thank you all.
Professor.